Welcome. This is a review for the third exam of Physics 111, Spring 2017. So, in this third exam, we are going to cover the following topics. We're going to do circular motion, and gravity, which is the content of chapter 5. We are also going to cover then rotational dynamics, that is the content of chapter 7, and by extension chapter 8, which includes equilibrium and elasticity. And third, the most important one of them all, not necessarily the biggest part of the exam, but the most important content of the semester, which is energy. So let's start. So let's start with our review of circular motion. So the first thing we are going to do is to remember that we're going to be looking at things that move around in a circle. And let us review the basic definitions associated with this motion. This particle that I have here is going to continue moving along the circle. We're going to choose this motion to go in the counterclockwise direction, but equally spaced. Later we'll see how this changes when we consider rotational dynamics, where the case when there is an acceleration along this path is more important to be considered. But right now we're just considering uniform circular motion. So let's start with this. This uniform circular motion has the following properties. The speed along the path is constant, so you have a speed phi, speed, and then you have an motion that occurs in a circle of radius r. And now we think about what's going to happen. So the object travels around the circle and returns to its original position. And when that happens, we call that the time it takes for this process to complete is the period t. We also have the frequency, which is the inverse of that period, with the obvious relation there. And finally, we are going to introduce right away, because we will use it later, the angular velocity or angular frequency, which is 2 pi over t. We mostly will use it later, and this is the angular velocity. So you should be able to go rather easily from one of these, from a combination of these variables to the next. For example, let us figure out the period if we know the velocity and the radius. So the total length of the circle is 2 pi r. That's the total displacement that you will have along the circle, and if we divide it by the period, then that has to be equal to the velocity. So that's a very simple relation that you should be able to figure out on the spot or as needed. Okay, so now let us find out the very important relation of these quantities to dynamics. So let's draw our circle again. And again, we have the object moving with some, let us redo that figure. We are going to erase this part because it's not well drawn. So even if the circle is not well drawn, we should be able to think about the velocity there, And now we are going to point out the following result that we obtained in chapter 3, and that is that since the velocity is changing direction, as you can see, that velocity vector is changing direction, and therefore we have an acceleration. The direction of the acceleration is at all times inwards. So we have the vector A, and the magnitude of that acceleration that we are going to give a special name is phi squared over r, where phi is the speed and r is the radius, and we call this the centripetal acceleration. The special names comes from the following fact. Whenever we look at this piece of curve, we have a vector of acceleration that might be in a general direction. However, it has two components in a special system of coordinates. One of them is tangential to the curve, and one of them is perpendicular to the curve. This tangential component is of course called then the tangential acceleration, and this one is the centripetal acceleration. So when we see the name centripetal acceleration, it just means that we are looking at that component, and if we are moving in a uniform circular motion, that one has only centripetal acceleration. It does not have a tangential acceleration since the speed is constant. Now that we know the acceleration of the in the uniform circular motion, we can solve problems that involve dynamics. Remember that in the dynamics of uniform circular motion, what we know is that, as usual, the net force is equal to the mass times the acceleration, but in this case we know what this one looks like. We know that the acceleration points inwards, and then we actually know also the magnitude if we know the speed of the circular motion. So we actually know everything here, and typically we are interested to connect that to the forces. Now the forces, the net forces, whichever forces they are going to add up to a net force that has to have also that same direction. So we did a number of examples of these. Let me just point out one of them, which is interesting. So we are going to do a loop-the-loop, where perhaps we are either in a roller coaster or in a Ferris wheel or something, so that we are going vertically in a circle, or rather that the circle changes your elevation. So when you're in the top of the circle and when you are in the bottom of the circle, you actually have a number of forces acting on you. But let's consider the simplest case, where you have, say, two forces, the weight and a normal force that perhaps is keeping you in your seat, and the net result of these two forces should be equal to a net force that points towards the center of the circle and has the properties dictated by this relation that we just wrote. So for example, in this case, we work it out, and setting up a system of coordinates that points vertically, we have the sum of forces in the y direction is going to be equal to the normal minus the weight, and is going to be equal to m and the magnitude of the acceleration, v squared over r. This will be true because the acceleration points upwards, so its y component is upwards. On the other hand, if we are looking at the top, then we still have the weight, But the normal, depending on the speed, it could point up or be 0 or point down. When you're going at high speed, it usually points down. In that case, in that second case, you have looking down, you have minus the normal, minus the weight, minus mv squared over r. That is the equation that we will solve to determine either a force or a velocity. So that's the most important fact to remember, is that this net force is a combination of all the forces, but to maintain your circular motion, that net force has to always point towards the center of the circle. The second topic in chapter 5 was gravity or gravitation. So it tells you that if you have two objects, and it is very easy and important to think of them as objects, large objects in space, maybe a planet and one of its moons. Then Newton proposed then that these two objects are going to experience an attractive force, which is the gravitational force. This is the force, the gravitational force of the moon on the planet, and this is the force of the planet on the moon. The moon. Okay, what's the magnitude of this force? It has a universal constant that sets the scale, because we measure things in distance and in whatever units of mass we have, and then eventually we want to get a force, so we need a constant that has that tells us the scale, the right scale of the force, and then the product of the masses, m1, m2, and the distance between the centers squared. These, by Newton's third law, these two forces are equal in magnitude, so you always know that they are the same. Let's see some applications of this. So one of the applications of this idea is that we can connect our typical way of thinking of the forces on an object near the surface of the Earth with that universal law of gravitation. So usually when we have an object near the surface of the Earth, we just think that we have a weight force acting on it, and certainly the object is pulling up the Earth towards it. What's the magnitude of this force? Then usually we write simply mg. That's the weight. On the other hand, we just saw that that force, the magnitude of the force, is given by the universal constant m. Then we have the mass of the Earth, the mass of the object, and the distance between them. And even if this object is a little bit elevated with respect to some to the surface of the Earth, really the distance is just approximately the radius of the Earth squared. So we compare these two magnitudes, and we obtain that the mg is equal to m gm over r squared, and we obtain what is the relation between our usual free fall acceleration g and the properties of the Earth. A second application of these ideas is orbit. So we have the sun and its planets, or the some planet and its moons, or some planet and its artificial satellites. So those satellites move approximately in a sorry about that. We have a circular orbit And now we want to use the gravitational law to study this orbit. So we have only one force acting on the satellite, and the satellite is going to be circling around the planet at a distance r from the center of the planet, so it's the radius of the orbit, and it's going to have some speed, and it's going to carry out this orbit in a period t. So let us write down Newton's second law. When we decompose along this direction, we simply have to write the net force, which is the only force we have, where capital M is the planet, little m is the mass of the satellite, and then the r is the distance, the radius of the orbit. So that net force has to be equal to the mass times the acceleration of the satellite. So that will be little m, and then v squared over r. So what we did, this is the second law along a system of coordinates that points towards the center of the planet, the center of the orbit. So let us solve, and then we obtain the following result. Again, the mass cancels because as explained by Einstein, these effects of gravitation really are nothing else but a reflection of the curvature of space. Therefore, it is not an independent, it doesn't depend on the mass. It's just the experience of an object in a certain place of the universe. So G m over r squared equals v squared over r. So we get v squared is equal, let's write it this way, gm over r. Let us write just one more equation here. Not there. V squared over r equals to, as you can see, sorry, we want to do v squared gm over r squared, so let's do it again, gm over r squared. So we have v squared equal to gm over r, and then we use the equations we wrote at the beginning. This is 2 pi r square over t square. Finally, 2 pi square r cubic, this is the important part, equals to gm t square. So the radius and the period have this power relation. R cubic is proportional to t squared. This is known as Kepler's law. Okay, let's go to rotational dynamics. For this, we are going to introduce right away our main concept, which is the Newton's second law, rotational dynamics version. So instead of having net force equals mass times acceleration, we have the torque, the net torque, equals the moment of inertia and the angular acceleration. So we claim that this is useful to describe the following systems. Anything that any object, no matter of its shape, if it is rotating with respect to this axis that goes into the page, So it's you should think of this as a three-dimensional system, but this axis does not move. It's like the center of the bicycle wheel, and then everything is going to rotate around that point. So this is a more complicated object because we want to consider what happens to every single element of it. So it's not just one object moving in a circle, it is the whole object rotating. So let's describe first the kinematics. So to do the kinematics, we remember the following relationships. One more time the circle. If we move in the circle and by an angle theta, well, if we move twice the an angle twice as big, then we're going to move a distance twice s. What's the relation between this angle and this distance? Well, they are proportional to each other. And if we choose the right system of units, if we choose the angle in radians, then we have s is equal to theta r, where r is the radius of the circle. So the speed is going to be equal to the change of that angle with respect to the time interval divided by the time interval and times the radius, or r omega. Omega is the angular velocity and is defined as the change of the angular position divided by the time interval. Same as the tangential acceleration, because that's how we are changing our speed along that circular path. So we do the same operation and we end up with the definition of angular acceleration. So that's the definition of angular acceleration, is the change in the angular velocity divided by the time interval. So that's our definition of angular acceleration. Please note that all these variables, all these angular variables and omega and alpha, are measured positive when it is counterclockwise and negative when it is clockwise. Okay. Uh-oh. Okay. I don't want that. Sorry about that. So we're going to do now moment of inertia, and this is very easy. It's simply the sum of the masses times their distance squared from the center of rotation. So you have a bunch of little masses, and then you just add the mass 1 times r1 squared, mass 2, mass 3, mass 4, etc. That's very easy. And then if you have something more complicated that is not just a system of little masses, you can use equations that I will provide you. For example, for a disk that is rotating, as you can see, this disk, this uniform disk, has little mass here, little mass here, everywhere has mass. And the net result is that the moment of inertia is 1/2 of mass times the distance, the radius square of the disk. Sorry. We're now going to do the third component of the second law, rotational dynamics version, which is torque. This is the more complicated of the most complicated of the three quantities that we need to define: angular acceleration, moment of inertia, and this one, torque. So the general setting is that we have the axis of rotation, also known as the pivot point, and then we apply a force and this projects in a direction that is parallel and perpendicular. So the torque is going to be defined as R F perpendicular. This is the one version of it, and we need to make sure that we know the sign. So in this case, the sign is going to be there is a way to determine the sign just from this construction, but let us simplify and simply think of this force that is perpendicular as a magnitude, and then we can add by hand a sign. The sign is positive if the rotation acceleration that we induce is counterclockwise, and is clockwise. If it is clockwise, then is negative. There are more ways to calculate this torque. The other way to do it is to consider that we have the force here, and then we extend that line of action. Whoa, okay, this is better. And then we have a distance r, not there, a distance r, and then we take the moment arm. This moment arm is going to be perpendicular to the line of action, and we are also going to call it r perpendicular. And then we simply say torque, again we give the proper sign, and it's r perpendicular F, and also RF perpendicular. So this is the hardest of our constructions. And just to give a simple example, remember that if we see a force that is, for example, vertical, then we can just take the horizontal distance here, and this is a simple way to calculate the torque. So it's going to be just tau r perpendicular F. This is the best way to calculate it when you have a force that is vertical or horizontal. Also remember that if your force is actually applied in a line that passes through the origin, then the torque here is going to be 0, because r perpendicular is 0. So after you are have mastered how to calculate all these things, then you can actually solve problems that involve the rotational dynamics of an object. So we can put a disk and we apply some forces to it like that, and maybe like this, and this torque is going to be 0, this torque is going to be negative, this also negative, and maybe another force here. So you calculate all the torques, and then that will allow you to determine the angular acceleration of the system. Of course, sometimes things are more complicated. You have to think a little bit more about the forces present. In chapter 8, the application of these ideas points out to the fact that if you want equilibrium, you need to have the sum of forces equals to 0, and the sum of torques equals to 0. The simplest application of these, as we did in lecture, was perhaps to consider a system like this. A simple plank. You put a pivot point here, and you apply forces at the ends of this bar, maybe say one here, F1, and then another one here, F2, and there has to be something supporting this, so a normal force here at that pivot point. Then R1, R2, then the equilibrium condition is that the sum of forces have to be 0, so we take the y components, and that will be n, magnitude of n, minus magnitude of F1 minus magnitude of F2 equals 0. Then we take torques. The torque of the normal force is 0 because that's our pivot point. We can always choose that one or any other. But if we choose this one, the torque of n is 0, and we just have to add the torques of F1, which is going to be positive, and the torque of F2, which is negative. The torque of F1 is R1 F1, so that's the torque 1, and the torque 2 is minus R2 F2, and that is 0. So these two are the equilibrium conditions for the bar, and as you can see, it allows us to determine a number of quantities here. So for example, if you know F1, you can determine F2 given the geometric information of the lengths of the two arms. That's the basic application of equilibrium. That's essentially the main idea in chapter 8. Now let's do chapter 10, energy. So we talked about the analogy between money and energy, and we said that we have a system, and in our analogy we have a fundamental form of money, which is cash, but now we're going to think of kinetic energy, and that can be converted into potential energy. Potential energy is the energy associated with the relative position of objects within the system. And then we can bring energy or extract energy in the form of work. That's when we apply external forces. And heat, that's when we also apply external forces, but we apply them at the microscopic level. And same the other way. If you identify the kinetic and potential energies at the microscopic levels, these have the name of thermal energy and chemical energy. The balance of energy is very simple. So you have the heat and the work, and that has to be equal to the change in the total energy of the system. Let's review the energies that are available. The energy can be kinetic, 1/2 of mass velocity square, speed square, potential gravitational, mgh, mgc, with respect to some reference point. And we have others. The spring is 1/2 of k x squared, where x is the length that we're stretching the spring, and k is the spring constant. So we can always calculate, or many times we can calculate explicitly what are the energies in an initial and final condition. And then we can also work out what is the work. The simplest case is when, what's that doing there? The simplest case is when we have a force and a displacement in the same direction, and then the work is simply Fd. If the force goes in the opposite direction, then we always take, then we can say is minus Fd, and if it goes in a general direction with respect to the displacement, we always take just the parallel component, which can be positive or negative. So the general formula is F parallel times D. So now we can do a standard application of the work energy theorem. Let us do this. Let's put a car on a hill, and we're going to give it a gentle push, and it's going to roll down, and we're going to assume there's no loss in energy, so there's no friction, and this elevation is going to be h, and I want to know what is the final velocity of the car. This is a standard problem. It's very easy to work out. Let us write our equation, and here we choose a system. So we're going to choose the following system. We're going to choose the planet and the car to be in the system. And if we do that, there's no work, because work requires the presence of an external force, and there's no other force coming in here to do anything, so it's all internal forces. So this is 0, and therefore we should have just the change in kinetic plus potential equals 0. That means that initial kinetic plus initial potential is K final plus U final. So we have that the initial is 0, that mgh is the initial potential energy, and this is half of m phi squared, and then we have 0 elevation at the end, so we choose that to be the reference point. Therefore our final velocity, as you can see, Einstein again shows up and tells us that the masses should not play a role, and therefore we have phi square root of 2gh. This is the standard calculation. In lecture we also look at another way to think about this, which is to actually calculate works. This is actually complicated in this particular case, but it's not so bad when you're, for example, dropping an object and you do not have a slope to worry about, and then you can actually carry out the same calculation, but considering, instead of potential energy, considering work. In the case the work done, for example, by weight, the magnitude of the weight is mg, so when you drop an object by a distance h, then your work is going to be mgh positive. So as you can see, you will have a work that is positive and a change in kinetic energy that is also positive, and it works out in exactly the same way. This concludes our review for our exam. Thank you.